Hello and good day everyone, my name is Ron and let us answer some sensitivity analysis problems. Create a rigorous distillation column with the following parameters with the compounds of acetone and water within the property package Raoult's law, where the inlet stream has these details: 360 kmols per hour, 0.7 acetone, 0.3 water, and 1 bar, with the different column configurations such as 13 stages, excluding total condenser, feed stage 8, reflux ratio 0.70611, and molar flow rate of bottoms is 106.53 kmols per hour. So we need to find the reflux ratio that corresponds to a mole fraction of water in the bottoms to be 0.99 with an error tolerance of 0.01. So we need to first go to DWSim, create a new process model, and follow the general direction or procedure for configuring a DWSim simulation process. So to start, we'll click next. We'll go here acetone and water. Next is the Raoult's law. Add. In the system of units, our customizable system of units. So we're given a pressure of bar. Double check. A pressure of bar. By the way, this is the given diagram for this problem. So pressure bar, and then molar flow rate is kilomoles per hour. And then temperature is not given, so we'll just put it as Celsius, and essentially that is it. So we'll finish, and then we'll now go to columns. This is the shortcut. We're not going to use the shortcut since we're required to do rigorous column. We'll put here distillation column function, and then we'll rename it as so for ease in identification. We'll put here DC for distillation column, 2 for feed, and this one for distillate, and this one for bottoms. And then the feed should be 0.7 and 0.3, except with an initial condition of 360 kilomoles per hour, 1 bar, and 25 Celsius, since it's just the standard for the DWSim. So it's 360 kilomoles per hour, 1 bar, 25 C, since there's no given temperature, 0.7 acetone, and 0.7 water. For the DC, the number of stages we'll put here, rather than 13, we'll put here 14, since we exclude the total condenser. I'll show you later. Total condenser at the top is same as the initial, which is 1 bar, and no pressure drop observed. Number of iterations, let's do 1000, since from my previous attempts on this problem, it had problems with 100, so I'll do 1000 with the conversion tolerance of 0.01 as follows. And then specifications for total condenser reflux ratio. Reflux ratio specified is 0.70611. Yes, reflux ratio. And then the boiler product molar flow rate is in kilomoles per hour, 106.3 kilomoles per hour. And then for the stages, that's the reason why I put here 14 rather than 13. It's because since the condenser is already considered stage 0, or not a stage, since it is a total condenser, not an equilibrium stage, that's why when I put here 13, it will only reach just 12. So when I put here 14, it will reach 13 stages. The connections. So I'll remove this. Since the feed stage is at the 8th stage, we'll put here feed port 8. And then the products, duties, and side draw stay the same. Stage stream association would be at stage 8. Side draw specifications. And essentially we are ready. So whenever we start, we can just solve the flow sheet. So it states here that DC reached the maximum number of iterations without converging. So we'll go back here, then we'll click here 1000 iterations, and now it has converged. So the bottoms is 0.7 and 0.3, and let to double check, we'll click here, we'll go to estimates and click all checkboxes and update automatically while clicking the refresh and solving again. Now, it is still 0.7, 0.3, so we have no error in the creation of this distillation column. The next step is for us to do a trial and error. However, we cannot do simply just input and output all the values that we can think out of our mind and input them in the DC configuration. We can just use a controller block. It is one of the specialties of DWSim. So the controller block allows this trial and error process to observe, and to do that, you get the logical block, controller block in the logical block section. And when you click on the logical block, you need to click on the value we want to change or manipulate. So we want to change the reflux ratio. We'll go to DC, and the DC specification is the condenser specification value, which corresponds to the reflux ratio, and it's its current value as I inputted earlier. And then what we want to aim is a bottoms molar fraction of water. So molar fraction of water at molar fraction mixture of water of 0.99 with a tolerance of 0.01 and a convert, and we'll click converge with flowsheet and solver. So set point 0.99, tolerance 0.01. Always remember to press enter before you do this so that it will be incorporated within the calculations. So as you can see, the lines are connected, everything is set, and we'll now solve. And as you can see, the iterations are happening. As you can see, the line is kept on repeating here and here. And though it may look incomplete or not solvable, as we go to the sorry about that. As we go through the specifications, it is still at 0.7, 0.3. So what happened? Why was it not connected properly? Well, what I suspect is let me delete this first. Is that the reflux ratio? Not delete first. Sorry. The reflux ratio initially stated is actually not applicable to. Creates errors. So what happens if I put 1 here and I change it to 0.98, and let's see what happens again. Now it is solvable, and here a water mole fraction reached 0.98 with a reflux ratio of 1. Maybe I need to check the estimates again. So let's do it again. So 0.99, so specification value is 1, 0.99. So what happens if I try to delete the block and just let it be as 1, specification as 1? Without the block, what is the 0.98, 942505? So let's go to estimates again. Let's recheck here. Click calculate. 0.98755 and re-update 0.988055. So at a specification value of 1. Then let's do again another controller block to double check. So it's the same procedure. So DC, it really is a trial and error with the trial and error logical block with regard when we're dealing with the condenser and a recondenser, the distillation column specification specifically. So just be patient, and you will try to you will try to be able to receive a value that is reasonable. So DC specification value controls bottoms of smaller fraction of water, molar fraction mixture of water. So we wish for a 0.99, and let's change the tolerance to 0.01. Let's see what happens. Alright, so the flow sheet was calculated successfully, and then what we calculate is here 0.9889. So there may be an error with the simulation, but even if I do the controller block again and again, it will still retain that the reflux ratio as it reaches 1 would have a bottoms of water at 0.98 or 0.99. I keep on repeating it, and it's not reaching 0.99, 0.989425. So when I converge it, the flow sheet solver, still the same, 0.99. Here now it's 0.99, and the specification is estimate. The specification is still reflux ratio is 1. So it might be a bit confusing in using the rigorous distillation column. It is a challenge actually compared to the other unit operations. But after doing the trial and error of the trial and error block, I can conclude that the reflux ratio, in order to reach a bottoms of 0.99, will require a reflux ratio of 1. So that's it. Feel free to double check on your own time if you wish to double check this simulation. Regardless, this is what the simulation yielded, and I conclude again that at reflux ratio when equals to 1, the bottoms would reach 0.99. Okay, so again, my name is Dayap. Thank you all for listening, and I'll talk to you all later.